Welcome back. This is the last trig ratio we're going to learn about, and that is the sine ratio. So sine ratio also corresponds to an acute angle in the triangle. So every angle has a tangent ratio, a cosine ratio, and a sine ratio. The sine ratio is the ratio of the opposite leg divided by the hypotenuse. This is in your notes. So the sine of an acute angle is the leg opposite the acute angle over the hypotenuse. So each angle has its own sine ratio, never increases or decreases, regardless of the size of the triangle. Same thing, by the way, with our cosine ratio and our tangent ratio. Even though the measure of the sides may increase, the measure of the angle does not change, nor does the ratio of side A to side C. The relationship between the sides remains unchanged. Right? So here we have the sine is the opposite over the hypotenuse. Right? Our last trig ratio. So let's find some sine ratios. All right, so when the sine ratio is written, always start with an acute angle as a starting point because we never start with the right angle. Suppose we want to find the sine ratio for angle A. Right, so that's sine ratio is the opposite over the hypotenuse. So for angle A, and I'll write in red, for angle A here, this side is the opposite, right, because it's across from the triangle. And this side is, side C here, is always going to be the hypotenuse. All right, so the leg opposite of angle A is leg A. Hypotenuse is side C. It's opposite the right angle. So the sine of angle A is A over C. What if we want the sine ratio for angle B? All right, so now we're starting over here. We're starting with this angle. All right, so now the opposite side for angle B is this side. All right, so side B is the opposite for angle B, and side A was the opposite for angle A. But no matter what, the hypotenuse is side C. So the sine ratio for angle B is going to be side B over C, the hypotenuse. Right? So let's take a look at this one. This one's in your notes, right? So sine is the opposite leg over the hypotenuse. We want to know the correct sine ratio for angle M. So across from from angle M is side M. So that's the opposite side, right? It's opposite angle M. And then, of course, the hypotenuse is always opposite the right angle. So the sine ratio for angle M is going to be the opposite side opposite angle M, which is side M, and the hypotenuse, which is side L. Right? So that's your sine ratio, and you can also circle number 2 here. Or if the circling is not in there, just write it down. I don't think the circling is in there, actually. Just everything else, now that I think about it. All right, so here we want to find the sine ratios for the two angles, angle R and angle S. So we've seen this triangle a lot. All right, so here is angle R. Opposite angle R is side 3 here. It's across the triangle. And of course the hypotenuse is always opposite the right angle. So the sine ratio for angle R is going to be 3 over the square root of 11. And of course we have to rationalize. So we'll multiply by square root of 11 over square root of 11, which is 3 square roots of 11 over 11. And if you remember correctly, that was the cosine ratio for angle S, interestingly. All right, so now let's find the sine ratio for the other angle, which is angle S. So we want this angle now. And so opposite angle S is this side. So now angle S is the opposite. But of course, the hypotenuse, that didn't change at all. So the sine ratio for angle S is 2 square roots of 11. Excuse me, thinking ahead. Is 2 over the square root of 11. Right, so the opposite side over the hypotenuse. We should write that in somewhere. Let's write it in there. So sine is opposite over hypotenuse. All right, so the sine ratio for angle S is going to be 2 over the square root of 11. And now we'll rationalize that, multiply it by the square root of 11 over the square root of 11, and that gives us 2 square roots of 11 over 11. And interestingly, the cosine ratio for angle R was the same as the sine ratio for angle S. Hope you find that interesting. I did. All right, so let's do a few more problems. And we'll do a couple more with sine, and then we'll mix them all together. All right, so here we have them all the sine ratios for these two triangles, and we've seen them a bunch. All right, and just as a reminder, and I think these are in your notes, let's write in sine is opposite over hypotenuse. All right, so first of all, we want the sine ratio for angle B. So angle B is right here. Whoops. And somehow, for reason, we have two triangles on top of one another there. Let's see if we can just get that thing to move. All right, so the sine ratio for angle B across from the triangle is the opposite side. And of course, oh, somehow my right angles got erased. Opposite the right angle is the hypotenuse. All right, so the sine ratio for angle B is going to be 10 over 2 square roots of 34. First of all, we could reduce. Both of those are divisible by 2. Right? So divide those by 2. 10 divided by 2 is 5. 2 divided by 2 is just 1. That gives us 5 over the square root of 34. And then we'll just rationalize by multiplying by the square root of 34 over the square root of 34. So now we have 5 square roots of 34 over 34. And that is the sine ratio for angle B. Now let's find the sine ratio for angle C. So now we want this one. So I'm going to move this out of there. But the hypotenuse is not going to change. Just which side is opposite. Because now this is the opposite side, the one on the other side of the triangle. All right, so the sine ratio for angle C is going to be the opposite side for angle C, which is 6, over the hypotenuse, which is 2 square roots of 34. And again, we could reduce. Both of these are divisible by 2. 6 divided by 2 is 3, and of course 2 divided by 2 is 1. So this is the same as 3 over the square root of 34. Of course, we don't want the radical in the denominator, so we'll rationalize by multiplying by the square root of 34, the square root of 34. So we have 3 square roots of 34 over 34. And there's our answer. And another one is done. Now this was a nice easy triangle, the one next to the other triangle. All right, so we're working with, first of all, sine angle E. So we want to find the sine ratio for angle E. Opposite is this one. Right? This leg is opposite because it's on the opposite side of the triangle. Right, so 2 square roots of 6 is the opposite. And of course, actually I'm going to write in black, change the color here. And of course, the hypotenuse never changes. All right, so the sine ratio for angle E is going to be the opposite side, which is 2 square roots of 6, over the hypotenuse, which is 5. All right, you can't reduce, and we don't care about the radical in the numerator. It's got to be somewhere, so numerator is good. All right, so now we want the final one, sine ratio for angle F. Let's move this, right, because that's no longer the opposite. Oh, I forgot I had a hypotenuse over here. That's okay, I wrote it in. All right, so now we're working with angle F. All right, so opposite angle F is this side over here. So now this one's the opposite. And that means the sine ratio, opposite over hypotenuse, is going to be 1/5. And we're done with this one. Another one done, right? We're just finding our trig ratios. We'll do other things with these trig ratios in later lessons, but right now, just finding the ratios. So here we're going to find the sine, the cosine, and the tangent ratios for each triangle here, right? And these are actually some very special triangles. Right? And so here we want the sine ratio, and we're finding it for angle A, all right? So we're not finding it for every angle, just for angle A. All right, so we have sine A is opposite. All right, so this side here is going to be the opposite triangle there. And Opposite the right angle is the hypotenuse. So the sine ratio here is 1/2. Cosine uses the adjacent side and the hypotenuse. So adjacent to angle A is this side here that makes that part of angle A. And so this is, we want the cosine. Oh, I don't want to put theta in. Well, I could put theta in there. Or I could put A. I'm going to put A. I put the theta in there to kind of mark where it was. But since we're really just talking about angle A, I think I'm going to put angle A. All right, so cosine for angle A is going to be the square root of 3 over 2. And then finally, the tangent for angle A, right, and I should put Jason here, is going to be the opposite side, which is 1, over the adjacent side, which is the square root of 3. And now this one we're going to have to rationalize because the square root's in the denominator. All right, so 1 times the square root of 3 is the square root of 3. Square root of 3 times the square root of 3 is the square root of 9, and the square root of 9 is 3. All right, so I will tell you that this is a special triangle, right? And we'll see what you discover about this triangle as we're solving measurements and we're working with triangles, but I won't tell you anything else. Let's look at this one. Now, this one is also a special triangle, but I think this one kind of gives itself away because it has two sides that are exactly the same, right? So that if we have two sides the same, we must have two angles the same. And since one is 90, that means there's 90 for each of these to share. This one is an isosceles. Right triangle. Right, since its angle measurements are going to be 45, 45, and 90, right, because that would add to 180 and give us two congruent angles opposite those congruent sides, it's sometimes called the 45, 45, 90 right triangle. All right, so let's find its sine ratio. All right, for angle A, let's label actually opposite and adjacent hypotenuse. All right, so opposite from angle A is this side here, which is 1. The adjacent side is the leg that makes up part of angle A, so this is the adjacent. And always opposite the right angle is the hypotenuse. So the sine ratio, there we go, for angle A is going to be the opposite side, which is 1, over the hypotenuse, which is the square root of 2. And we'll have to rationalize this. So multiply by square root of 2 over square root of 2. That will give us 1 square root of 2. So 1 times the square root of 2 is just the square root of 2. And the square root of 2 times the square root of 2 is the square root of 4, which is just 2. Cosine for angle A. All right, now we're using the adjacent side. Of course, the adjacent side is also 1. So guess what? We're going to have the exact same answer, which makes sense because the sides are the exact same measure. All right, and then finally, we want the tangent ratio. And the tangent uses the opposite side, which is 1, over the adjacent side, which is also 1, which is just 1. Isn't that interesting? All right. And I know this might be, I think I have one more for us to do. And we're just going to find the sine, the cosine, and the tangent ratios for one more pair of triangles. Right? And I will tell you these were both special triangles. We already learned why the one on the left or the right was special. We didn't learn too much about the left one yet. But these ones, no particular triangle, just triangles. They happen to have sides that are all integer values, which means they are Pythagorean triples. But other than that, there's nothing else special about these triangles. And this is in your notes. All right, so let's find the sine ratio for angle A. All right, so here's angle A. Opposite angle A is right here. Right, and then, of course, making up part of angle A is the adjacent side. And then opposite the right angle is the hypotenuse. Always a good idea to label your sides first, then you won't make a mistake with which side is which. So the sine ratio for angle A is going to be 7 over 25. No reducing there. The cosine ratio for angle A, right, it's just a reminder that, let's put it over here. So sine, just a reminder, is, and you don't have to write this down, you have it all through your notes. But let's just put it up here so that, oops, what am I writing adjacent? I'm thinking of cosine, which uses the adjacent. I just want us to remember our, and really I should have an angle in there. The cosine ratio, just a reminder there, it uses the adjacent side and the hypotenuse. And finally, the tangent ratio for an angle uses the opposite and the adjacent. That way we can have it right on the page as we're talking about these. All right, so the cosine ratio for angle A, right, we'll use the leg adjacent to angle A, which is 24, right, over the hypotenuse, which is 25, and that is in reduced terms. And then tangent is the opposite side, which is 7, that's opposite angle A there, and the adjacent side, which is 24, and that doesn't reduce either. All right, so we're done with the first triangle. Let's try the second triangle. All right, so now the sine ratio we're looking at angle A here. Let's label our sides. So on the opposite side of the triangle is the opposite leg. The right angle got erased here, but there's the right angle. And opposite the right angle is the hypotenuse. And of course, adjacent to angle A, the leg that makes up part of angle A, is the adjacent side. All right, so sine uses the opposite and the hypotenuse. All right, so the opposite side is 21, and the hypotenuse is 75. We could reduce those. All right, they're both divisible by 3. All right, so 21 divided by 3 is 7, and 75 divided by 3 is 25. Hey, that's the same thing we got for the other triangle. Look at that. 7 over 25, 7 over 25. How about that? What a coincidence. All right, so now the cosine ratio is going to use the adjacent side, which is 72, over the hypotenuse, which is 75. And hey, these are both divisible by 3 as well. 72 divided by 3 is going to be 24. And 75 divided by 3 is going to be 25. Hey, that's the same as the other triangle. Boy, a lot of coincidences here. All right, let's find the tangent ratio. All right, so the tangent ratio uses the opposite side, which is 21, over the adjacent side, which is 72. And these are both divisible by 3 again. So 21 divided by 3, that's 7. And 72 divided by 3, that's 24. And who would have thought it? Look at that. We got the exact same ratio. Wow, how these coincidences are happening? Well, maybe you read this little thing up here. Put this in your notes. So you get this, when you get the same trig ratios, it means the triangles are similar, right? Because the sides are going to reduce to the same ratio. So same trig ratios, you have similar triangles. And so now we've learned another way where we're going to be able to figure out if triangles are similar. And that's the end of this podcast. So thanks for learning about some trig ratios. In the next lesson in class, we're going to be doing some advanced problems with trig ratios. We're still not solving yet. We're just working with our trig ratios, but we'll learn how to do a few more things with trig ratios. All right, thanks for watching, and bye for now.